Okay, in this video we will talk a little bit about recursive sequences. Recursive sequence is a sequence laid out right here where subsequent terms are defined by using previous terms. It's a little vague, so here's what I mean. Basically, if you look at this quick little sequence, 1, 3, 5, 7, to describe it in a recursive manner, to give it a recursive description, it is add 2 to the previous term. Now, what you'll see in this is that recursive sequences, to describe something recursively, it is a bit easier to describe something recursively, but they tend to be less useful in the grand scheme of things. So there are some obvious limitations. For instance, if we wanted to find the 100th term of this sequence right here, so this is a sub 1, this is a sub 2, a sub 3, a sub 4. If we wanted to find the 100th term, we would need to know the 99th term. And in order to know the 99th, you would need to know the 98th, etc. So it's got some obvious limitations, but definitely some interesting things can happen when defining something recursively. Now, real quick, before we move on to a couple of examples, to describe this, go back to the words. Add 2 to the previous term. Well, if we're trying to write it in terms of a sub 1, here's where an interesting notation comes in, and it's an important thing. If you're describing the a sub nth term, so for instance, if you're describing the 5th term, you need to describe this as the 4th term plus 2, because this would be the 5th term. The next one, 9 here, would be the 5th term is the 4th term plus 2. So in this case, a sub n would be the a sub n minus 1 plus 2. Or you could describe it as a sub n plus 1 equals a sub n plus 2. In other words, the 4th term plus 2 gives you the 5th term. So those notations, super important. So keep those in mind as we go forward. So let's look at a couple of examples of some recursive sequences. Here we're defining the first term of the sequence. And we're defining the next term based on the first term. So here we got that n plus 1 business. So what you have here is what this is saying is that the second term is the first term plus 2. So 32 plus 2 is quite simply 34, except for the fact that it's plus 2. It's not plus 2. So ignore me for just a second while I fix this. A sub 1 minus 2 is obviously 30. And then a sub 3 will be a sub 2 minus 2, so that's 28. And writing it out in notational form is actually a little more difficult than actually just figuring out the numbers. Because you can just continue subtracting 2 forever and ever and ever. So the 4th term was the 3rd term minus 2. The 5th term was the 4th term minus 2. So what you can see is the second term here being 30, matching up with 30 minus 2, just like that. And then the third term, 28 minus 2 gives you that 26. And then the fourth term being 26 minus 2, etc., and on down the line. Again, I spoke of obvious limitations of these things. The obvious limitations of a recursive sequence, well, again, I like to go back to this. What's the 100th term? Well, it's the 99th minus 2. Do we know the 99th? No, we don't. We'd have to know the 98th, the 97th, etc., etc., etc. So yes, it's easy to generate a sequence and describe a sequence recursively, but the usefulness is a little less than an explicit sequence. Okay? So, let's do one more example of a recursive sequence, and this is one of the most famous sequences in mathematical history. It's started off, the first term is 1, the second term is 1. Pretty easy. And then this is the, quote, formula. This is the recursive formula that describes this sequence. So what this is saying is, well, we already have the first two terms. So let's try to figure out the third term. So if n is 3, so if n equals 3, what this recursive formula is saying is it's the previous term. So 3 minus 1 is 2, plus, well, 3 minus 2 is 1. So this, the third term, is the second term plus the first term. 1 plus 1, which is obviously 2. So the third term is 2. So now let's think this. First term is 1. That's this guy. And the second term is also 1. So that's this guy. Now the third term is, of course, 2. Pretty basic. Now, let's go find the fourth term now. Fourth term is the previous term plus 2 terms ago. So I need a sub 2, and I need a sub 3. And that will give us 2 plus, in this case, 1, and that'll be 3. So that's the fourth term. And I think you get the idea. A sub 5 will be the fourth term plus the third term, and that gives you 3 plus 2, and that will give you 5. And then the sixth term, because we are finding the sixth term. The sixth term is the previous 2 terms, so that'll be 5 plus 3. And that's 8. So if you lay out this sequence, 1, 1, 2, 3, you can see the sum of these two is 5. Sum of these two is now 8. Some of these two is 13, some of these two is 21, 34, etc., etc., etc. As I mentioned at the beginning of this example, this is one of the most famous sequences ever to exist. It's called the Fibonacci sequence. And it has to do, it generates, it's called the limit, whatever, we'll talk about it at the end of the year. It generates something called the golden ratio, or phi. It's a Greek letter. It's approximately 1.61. Something, something, something. And it's considered to be the most beautiful number. And what happens is if you take the ratio of successive terms, if you did 3 divided by 2, you'd get 1.5. 5 divided by 3, you would get 1.75. I'm sorry, 1.6 repeating. 8 divided by 5 is now 1.8. 13 divided by 8 is a little bit closer. So as you go through these Fibonacci numbers and start doing successive terms, 34 over 21, and then you're getting closer and closer to this golden ratio as you go on down the line. Okay, so that's how recursive sequences work. But before we go on to the next topic, which is going to be the next video in this playlist is all about factorials. Let's just review all of the notation that's involved in the sequences that we've talked about so far. So you see these n's and a sub n's and all this kind of stuff. Just keep it away. Just keep it straight in your mind. It'll help out a lot. These are all just general terms. This is usually the term number, and this is usually your term value, your input, and your output. And these notations usually come with recursive sequences. What you can think of is a sub n represents your current term. So if you're talking about a sub 4, talking about that makes your fourth term, that's where you currently are. A sub n would be your previous term. So in that case, if you're sitting here at a sub 4, well, the previous term would be the third term. And then the n plus 1, you can think the word next, and so that would be your fifth term. So keeping your notations squared away is an important feature.